Recall that when you and I generated a technique for computing arc length earlier this semester, we partitioned the interval from A to B into n subintervals of equal length, and we approximated a portion of the length of the curve over the ith arbitrary interval with ds. We drew a nifty little triangle. This came from the Pythagorean theorem. If you multiply top and bottom by dt, treat them as differentials for a brief moment. We see ds as this. Now going back to derivatives, not differentials, that's what I have in these two sets of parentheses. Taking the limit of the Riemann sum, then the length of an arc along a curve described parametrically can be computed by looking at the integral from alpha to beta of the square root, the sum of the squares of the derivatives for x and y with respect to t. But of course, we'll be integrating with respect to t. Let's put this to use. Going back, oh shoot, but I forgot how we described the curve. I think this is correct. Oh my goodness. I hope so. So the arc length. Sorry, can I rephrase the question? Let's compute the length of the curve that creates that loop. So obviously, as t ranges from -1 to 1, here's my standing ground position. That's dx dt. That's dy dt. So if you don't mind, I'm merely going to set it up. And so I set up an integral that does indeed represent the length of the loop that I created with the first example I had for the interval analysis technique.